Good morning, everyone. Yeah, I don't think Blackboard wants me in class, so I'll go ahead and take a vacation. That's cool. Be careful with our answers up on our content questions because I am seeing some mistakes up there, so just be careful with that. And obviously in the chat box, write in what your favorite book is. There's so many good books out there right now, and I'm seeing those books flying up. Yeah, we seem to be arguing over vertical velocity. We're going to go through that. So just kind of see who is correct. There's kind of a tie here. I see a tie here. Excellent, excellent. All righty. I'm currently reading a book right now. It's called, and maybe you all have heard it, Keeper of the Lost Cities. I'm on, I think, book 4. It's a huge series. It's a kind of a cross between a Harry Potter and, I don't even know, it's a little Harry Potter-ish, but it is sci-fi, it's fantasy, all wrapped up into one. I don't know if any of you have heard of it. Your mom's reading that one right now, Regina? Yeah, it's a really good series, and it's about this girl who is actually an elf, but really grew up in like our world as a human. Yeah, that's a crazy coincidence. Yeah, and it's for like middle grades, some some high school kids enjoy it. A really good read, by the way, though. But yeah. Awesome. All right, so let's go ahead and look, since it is the start of class, let's go ahead and resolve this fight over vertical velocity. So first of all, let's talk about what projectile motion is. Remember, we talked about this yesterday, and we have a couple of different things that we have to look at. First of all, we have to look at our horizontal path. And so when we look at our horizontal path, we're looking at this one, the left to right horizontal path. This is our gravity-free path. Remember, if there was no gravity, where would the ball go? It would have that constant velocity, that constant movement, and it would go on forever and ever, Newton's first law of motion. So when we look at that vertical or horizontal motion, there is no horizontal external force. Just like I said, it's gravity-free, no gravity, so that one is correct. Awesome job on that one, horizontal external force. Now, when we look at our vertical force, though, we do have a vertical force, and that is our up and down. That vertical force, obviously, is going to be our gravity. That's what's pulling that ball down, or the cannonball. And so that vertical or external force is gravity, and so you got that one correct. Now, looking at these numbers here, and this is what's going to help with our velocity here, is our horizontal velocity are these numbers here, 20 meters per second, okay? Now, when we look at these numbers, 20 meters per second, what do we notice about these numbers? Let me know in the chat box. What do we notice about these numbers? Do they decrease, increase, or do they stay the same? Yeah, they stay the same. Excellent. And the reason because they stay the same is because, again, there is no horizontal external force, no gravity to pull it down. Now, looking at this one, the vertical velocity, the one where we're arguing over, well, if you look at these numbers, this is vertical velocity right here. We notice that what are these numbers doing? Starting at the very top, going down to the very bottom, what are they doing? Let me know in the chat box. What are these numbers right here? Yeah, they go. Are they going down? They have a 9.8 all the way up to a 49.0. Yeah, exactly. Regina, you got it. Haley, you have it. Yes, they are increasing. Obviously, when you drop a ball off a cliff and you only have the one external force, which would be gravity, you have that external force, it's going to start increasing in velocity. And so increasing in velocity is our answer here. So those of you who said decreasing, sorry, it would be increasing. And those that say the same, I think you were getting confused with horizontal versus vertical, but we're looking at the vertical. It increases. The velocity does increase as the ball is dropping. And we have that external force of gravity. So nice job, everybody. Let's go ahead and kind of go through our schedule really quickly. We do have a lot of stuff to get through today, so make sure that you are Participating and respecting peers, often and well. Remember that this class session is recorded and distributed for learning purposes. Please do not share any personal information or information of others into the chat box for your protection and the protection of others. All right, so with that being said, it is day 14 of our 60-day adventure. It is September 9th, and we're going to be working on gravity and motion. Part 2, we're going to talk about free fall and calculate some velocity due to free fall. We're going to do this through our 2H assignment and obviously our attendance discussion. We're rounding out Unit 2, so we only have a couple more lessons to go through, and then we will round out with our Unit 2 project, which we'll talk about today. Again, we're going to talk about the effects of gravity on objects in free fall due to Newton's second law of motion. And we're going to calculate, just like I said, some velocity of an object in free fall on Earth. All right, with that being said, I'm going to go ahead and grab our links. I think I already did. Excellent. And I'm going to place them up in the chat box. Go ahead and start opening up those links. I know some of you are such quickie quicks. They've already have opened up their assignment, so give me that green check loud and proud that you have opened up your assignment. We do not want to leave anybody behind here, so open up those assignments. Again, we have, let's see, we have 29 of us. I would love to see full attendance or full participation here, so let's get those assignments open. I know, Antoine, I know you'd love to give a double green check. Let's get those assignments open. Let's be participating. Again, the faster you participate, little hint of the word, faster you participate, the better. As you're opening up those assignments, folks, a couple different things that we've noticed with attendance. Make sure you stick around for the attendance question at the very end, and please make sure that you're answering the attendance question. I've been getting some kind of random answers. That does not give you attendance. Make sure you're answering the attendance question at the very end. Mrs. Larkin will go through that yet again at the end of class. All right, let's get those green checks in. So I'm going to check in with Alec, green check. Angelo, green check. Isaiah, green check. Jaylyn, green check. Tyon, green check. Madison, Matthew, Moises, Monique, green check, please. Awesome job. All right, let's go ahead and move on.
All right, well, you couldn't hear me, so let's try that again. All right, in the chat box or on the whiteboard, I gave you your tools back. If you drop a brick and a feather at the same time, which one hits the ground first, and tell me why. All right, so we should probably be able to all come to an agreement on which one hits the ground first, but which one hits the ground and why? We need to have a explanation. Go ahead, get your answer in the chat box or on the whiteboard. We got a feather, a brick. If we drop them at the same time, what's going on? Rishane's playing in the chat box. Looking good. All right, looks like we're all agreeing for the most part that the brick is going to hit first. And again, give me some explanations why in the chat box or on the whiteboard. Looking good. All right, so we have some different explanations. We say it weighs more, right? Someone's just saying gravity, right? So maybe it has more mass. The feather floats away, so maybe it's just because the feather floats away. Slow and steady wins the race. You're funny. All right, very cool. So it looks like we have some different explanations here. So that being said, I would agree the brick is definitely going to hit first, but today we're going to see that there's actually an interesting reason why the brick hits first and the feather does not. And it actually is going to be a little bit different than you might originally be thinking based on what we just brainstormed. So remember that the force due to gravity is also called weight. So for example, when you weigh yourself on a scale at home, what you're actually measuring is how much gravity is affecting you, right? The equation for force is mass times acceleration, and therefore the force due to gravity is mass times the acceleration due to gravity. And again, we could also call this weight. Now, what this means is that when objects are in free fall, so falling through the through the environment, they are only affected by the force due to gravity. So if they're only affected by the force due to gravity, then they all have the same acceleration, the acceleration due to gravity. And if all objects on Earth accelerate at the same rate, that means that they speed up the same amount, which means that if you drop them from the same place, they actually hit the ground at the same time. And this is what Galileo Galilei's Leaning Tower of Pisa experiment proved. How many of you have ever heard of this, or heard of this experiment, or seen the Leaning Tower of Pisa, a picture of it, maybe in person? I saw it in person a couple of years ago. It was pretty awesome. Got to take a nap in its shade. Yeah, awesome, cool. So what he discovered is that if you take a 1,000 kilogram mass or a 1 kilogram mass, really doesn't matter. If you take two different objects of different mass and you drop them from the same place, because they experience the same exact acceleration, they actually hit the ground at the same time. So based on this, based on what Galileo saw, does the mass of the object matter? If a 1,000 kilogram mass and a 1 kilogram mass hit the ground at the same time, does their mass matter? Does their mass matter? Yes or no? Tell me in the chat box. No, their mass actually does not matter at all. So I'm going to write this right here because that's really important. Mass does not matter, which means that when we were thinking about the brick and the feather, the fact that the brick is heavier and has more mass is not actually important. All right, so in reality, that has nothing to do with how things fall. The only thing that has anything to do with how things fall is the force of gravity, and therefore the acceleration due to gravity, which is the exact same for all objects. It is negative 9.8 meters per second squared. I need you to commit that to memory because you are going to be asked this several times during class today. So go ahead in the chat box, tell me again, what's the acceleration due to gravity on Earth? Everybody should know this number by the end of class. Type it, that way you get used to it. Type it, that way you get used to it. Oh, Greta, you've been there. That's awesome. What is the acceleration due to gravity on Earth? This is the magic number. Give it to me in the chat box so you can get used to typing it. Yeah, negative 9.8, and I love seeing those units, meters per second squared. Beautiful. But here's the problem. We just decided that a brick definitely hits the ground faster, and I agreed with you on that. So what is actually going on with our brick and our feather? So I'm going to go ahead and show you this awesome video that blows my mind every single time. Let's go ahead, watch this. Give me a green check when you finish watching it. I will also drop the link in the chat box if it does not show up for you on your whiteboard. Here we go.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exact. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side. I'll let the
Exactly the
folks
same.
see the
Feathers don't move, nothing.
Look at that. That's just brilliant.
Green checks if you finished the video. Excellent. All right, those green checks are rolling in. All right, cool. So let's go ahead and start out with the first drop, the one that seems pretty normal to us on Earth. What happened in the first drop? Yeah, I love this video. It's definitely one of my favorites. I have another Mythbusters one, which is probably my other favorite one. Haley, we haven't gotten to questions 1 or 2 yet. Don't worry, we'll let you know. Yeah, so in the very first, yeah, it's still up here because you can actually rewind and take a look at what happened if you want to. So I always kind of leave it up there for a little bit so that everyone can make sure they see it. So what happened in the very first scenario? I've got one answer so far from Melissa. Let's get some more participation in the chat box. Awesome, Lisa, I see your answer. Very good. Yeah, so in the first scenario, that was pretty much what we expected, right? Thinking about our brick and feather brainstorm. I see Harmony's got a similar answer. Yeah, the bowling ball fell a lot faster. The feathers just kind of floated around like someone mentioned, and so they did not go very quickly. What about in the second scenario, though? After they removed all of the air from the chamber, which is just wild to think about, so they took out all of the oxygen, all of the nitrogen, which is what air is mostly made up of, and then they dropped them. What happened then? What happened then? And again, it's so mind-blowing to watch it. Yeah, they actually fall at the exact same time. The feather and the bowling ball, you saw, kept track with each other the entire time and hit that box at the exact same time. So what that tells me is, tell me in the chat box, are the feather and the bowling ball the same mass? Yes or no? Do they have the same mass? Yes or no? No, definitely our bowling ball is way heavier, has way more mass than our feathers. But did that matter in our second scenario? Did the mass of the feather and the bowling ball matter at all in our second scenario? No, not at all. They both hit the ground at the same time, just like Galileo predicted that things will fall at the exact same acceleration due to gravity, and they will hit the ground at the same time. Now, the only reason that in real life, and I know that Antoine hit this on the nail on the head, the only reason that things do fall at different rates in real life is because there's actually a second force in play. And anytime you have another external force, this changes what we see. So air resistance is another external force, and this force is opposing the motion, specifically of things that are really spread out, like a flat piece of paper versus a crumpled piece of paper. The flat piece of paper will actually take longer to float down, same thing with a feather, and this actually has to do with the shape of the object and not the actual mass of the object. So air resistance is opposing the motion of an object based on its shape, and this actually reduces the object's acceleration. But again, the physical mass did not matter once we removed the air resistance. So physical mass has nothing to do with the rate of falling. This is number 1 on your notes. Give us a green check when you have this saved. Please go ahead and fill in the blank with the word accelerate. Go, go, go. 30 seconds. Make sure you spell it correctly. 15 seconds remaining. I got about half of my green checks. And 5 seconds. All right, Timothy, Natalie, Monique, Moises, Luis, Keon, Harmony, green checks, please. We're moving on in 5, 4, 3, 2, 1. All right, if you missed it, you'll have to go back to the recording around 1 to 2 p.m.
Alrighty, so let's take a look at this. Let's practice a little bit of this. Let's change our polling tools to our green checks to polling tools, A, B, C, or D, and there we go. And with that being said, let's look at number 1 here. What is the acceleration due to Earth's gravity on a 20-kilogram ball? Is it A? Is it B? Is it C, or is it D? Lock in your answers. Let's take a look at this, and I will give you a hint. Acceleration due to Earth's gravity, the magic number. The magic number. Go ahead and lock in your answers. I'll give you another 5 seconds. 5, 4, 3, 2, and 1. Let's send it right there. And let's go ahead and publish our whiteboard tools, our polling tools. And yes, hands down, I agree with everyone out here. That is correct. B is the correct answer at a negative 9.8 meters per second squared. So let's take a look at question number 2. What is the acceleration due to Earth's gravity on a 200 kilogram ball? And I'm going to clear these out. Go ahead and lock in your answers. I'll give you 15 seconds. Is it A? Is it B? Is it C? Or is it D? Again, 15 seconds up on the clock. Lock in your answers. We're giving a little hint, the magic number, acceleration due to Earth's gravity. A lot of people are getting a little confused. Alrighty, Regionette, listen very carefully. I will tell you that magic number, and here we go. And so, publishing our whiteboard, or our results here, yes, I agree. Again, looking at this one, a couple of people did pick B. Be careful, it is not D. It is going to be B. Again, our magic number is B, and negative 9.8 meters per second squared. This just says, just like we watched in the video, mass does not matter. Okay, mass does not matter when we're talking about the acceleration due to Earth's gravity. It is a constant at a negative 9.8 meters per second squared. That is your magic number. All right, so let's look at number 3 here, going through this very quickly. If both objects have the same acceleration due to Earth's gravity and are free-falling with no air resistance, think of our video, think of the second time they did the experiment when they got rid of all the air, so no second external force. Which hit the ground first? Which hit the ground first? Is it A, and I'm going to go ahead and clear these out just in case. Is it A, the 20 kilogram object? Is it B, the 200 kilogram object? C, they hit at the same time? Or D, neither hits the ground? 15 seconds to lock in your answers. Go, go, go. Yes, Daniel, we will go over the 2 of us in class. I have 16. I need to see a little more green checks before I can move on. Excellent. Just checking in with a few people here. Aiden, just checking in, making sure you get a green check. Angelo, green check. Daniel, green check. Again, if you have any questions, let us know in the chat box. Kion, green checks. Matthew, Moises, Monique, Nathan. Green checks. Let's go ahead and get those in there. All right, here we go. Let's move on.
All right, so now we're going to go ahead and actually apply what we just learned to an equation, because the cool thing is that based on this, we can actually determine the velocity of an object without actually ever measuring the velocity of an object. So what we can do is, if we know the acceleration due to gravity, which is our magic number, and if we know the velocity it starts at and how long it takes to fall, you can actually solve for final velocity without ever having to use a measuring tool to solve it. All right? Yeah. So let's go ahead and see here. We want to solve for the final velocity. So I'm going to rearrange this equation. In order to solve for a variable, we want to get rid of what's ever next to it, starting from what's furthest away from it. So furthest away from it is dividing by time, and the way that we get rid of something is by doing the inverse. What is the inverse of dividing by time? What is the inverse of dividing? The inverse function of division. Tell me in the chat box, everyone. We should know this one. What's the opposite or inverse of dividing? Yeah, multiplying. So I'm going to multiply by time on the right side of my equal side, but whatever I do to one side, I also need to do where? Yep, also on the other side. So remember that what this ends up doing is when you do an inverse, it gets rid of it. So now our time is gone and it's now on the other side. So let's go ahead and pull this down. The acceleration due to gravity times time is going to equal our final velocity minus our initial velocity. Cool. So now I need to just get my final velocity again by itself. And now what's next to it is subtracting initial velocity. What is the inverse or opposite of subtracting? If I want to get rid of subtracting the initial velocity, what would be the inverse or opposite function? Perfect. Yeah, I'm just going to add it. All right, but whatever I do to one side, I also need to do. Yeah, to the other side. So I'm also going to add initial velocity to the other side. But on my first side, this actually ends up canceling out. And so now all I'm left with is my final velocity. So if I were to write this out, on the left side, I have the acceleration due to gravity times time plus the initial velocity equals my final velocity. All right, so that all looks good and everything, but you will notice that I actually rewrote it down here in reverse just because we read from left to right, and so that makes it a little bit easier visually for us to see. So this is literally staying the same thing, right? So final velocity still equals the initial velocity plus the acceleration times time. So that's how we got our equation for today. You don't need to know how to derive it. You just need to know and understand that equations are related to each other. Give me a music note if you understand how we got from A to B, how we got from this starting acceleration equation to this final velocity equation. Beautiful. All right, so now let's actually begin to use it. What is the final velocity of an apple that starts at rest and then free falls on Earth for 3 seconds? Now, if you take a look down here, when we fill in our final velocity equation, we need to have 3 numbers. And currently, I only see 1 number up here. So I'm going to do some annotation and try to see if we can find some other numbers. So here we go. Starts at rest. This can actually be a number. Starting at rest, what is the initial velocity of an object that starts at rest? The initial velocity of an object that starts at rest is, yeah, exactly. It's just 0 meters per second. Try to make sure you use those units. So the initial velocity of something that starts at rest means it's not moving. It has 0 meters per second of velocity. Then it falls for 3 seconds. Seconds tells me what? The unit seconds is for what? Is that a initial velocity, acceleration due to gravity, or time? Yeah, this is our time. Good. So T for time, I'm going to label that. And then again, the third number you actually know is your magic number. What is the magic number? Acceleration due to gravity equals what? Negative what? Acceleration due to gravity equals what? Yeah, it equals negative 9.8 meters per second squared. So there we go. We actually do have 3 numbers. Let's go ahead and fill it out. Thank you, Haley and Rowan, for including those units as well. That's always good practice. What should I plug in for my initial velocity based on what we just annotated? What do I plug in for my first blank initial velocity? Just give me the number. Yep, we're going to plug in 0. What do I plug in for acceleration due to gravity in my second blank? Again, right now, just give me the number. Negative 9.8, not 3. 3 is not the acceleration due to gravity. 3 is the what? What do I plug in for time? What do I plug in for time? Yep, perfect. 3 is going in for the time. So here we go. We need to do what's in the parentheses first, or in other words, always start with multiplication. So negative 9.8 times 3 equals, negative 9.8 times 3 equals, grab a calculator, grab a phone, or type in the word calculator into Google, and a calculator will pop up. I know, we're moving faster, so don't worry, don't worry. We're going to practice it a bunch too. Yep, negative 29.4, good. And over here, I'm just going to keep this at 0. And 0 plus a number, 0 plus negative 29.4 still equals what? 0 plus negative 29.4 still equals what? Yeah, it still equals negative 29.4. Perfect. So this is the correct answer for number 5. You will notice, however, that your answers for number 5 are only positive because Mrs. Larkin had a brain fart this morning when she was making the assignment. So the answer should technically be negative, but you'll notice that in your assignment you only have positive options. So for your assignment, choose the 29.4 meters per second as your answer for number 5 and give me a green check. Here we go. You have 20 seconds. This one should be fast. Go, go, go. Yes. We also like to call that mommy brain because once you have a child, everything just kind of goes out the window. 10 seconds. All right, waiting on Angelo, Chad, Greta, Harmony, Isaiah, Ivana, Jade Lynn, Jalen, Jorge, Kian, Luis, Matthew, Moises, Monique, and Timothy. Again, I know our correct answer should be negative because the object is falling and going down. But remember that your assignment, I only gave you positive options, so choose positive 29.4. Cool, thank you, Brisa, you're so kind. All right, so what is the final velocity of a phone that starts at rest and then free falls on Earth for 4.5 seconds? This one's really sad. Same thing here, let's annotate starting at rest is what? Starting at rest is what? Yeah, and falling for 4.5 seconds, you actually have to be really high up for that to happen. So that phone's definitely going to break. Yeah, this is our 0 meters per second, so that's our initial velocity. 4.5 seconds, seconds is time, yes, and our magic number, acceleration due to gravity, is, yep, negative 9.8. Beautiful. So plugging this in, for my initial velocity, what number should I put in for my first blank? Right here for my initial velocity. Beautiful. Beautiful. Yep, 0. What number should I plug in for my acceleration due to gravity? The second blank, based on what we just annotated. Love all the participation, negative 9.8. And what about my last one for time? I think this is when students are the most awake because period 3, y'all are on point when it comes to participation. Yeah, this is 4.5 seconds. Beautiful. All right, so I want you to go ahead and actually calculate all the way to the end what is the final velocity of our phone here. All right, so make sure you do the multiplication first, then add 0. What's the final answer? I know, my stomach is currently rumbling right now too. Excellent. I see Lisa. I see Brisa. I see Alyssa. Got it. We have a lot of Issa names right now. Perfect. Greta there. Perfect. Yeah, you should be getting negative 44.1. If you're not sure how we got there, what we did was negative 9.8 times 4.5. Do that first. So that does equal negative 44.1. And when you add 0 to that, that still equals negative 44.1. This is the answer to number 6. Again, the answer should be negative because it's falling, but Mrs. Larkin made it positive in the assignment. So just choose 44.1 so that you still get full credit. 20 seconds. Go, go, go. Green checks, everybody. Work quickly. All right, I have 15 green checks. Need about 15 more. So Alec, Angelo, thank you, Angelo, Antoine, Bowen, Chad, green checks, please. Haley, Harmony, Isaiah, thank you, Ivana. Waiting on John, Keon, Luis, Matthew, Moises, Monique. Green checks. I feel like I'm saying the same name so frequently. That's interesting. All right, let's go ahead and do this last one. Don't guess on the last one. What?
Alrighty, here we go. Period 3 on point. Let's look at this. This is a complete on your own, so I'm looking at the quiz right now, and the question is not up there like every other one. So let's look at it. What is the final velocity of an egg that starts at rest? Remember, starting at rest, what that would be, and then free falling on Earth for 2.7 seconds. Remember the acceleration, our magic number. And you're obviously looking at seconds here, we're dealing with time. So with that, go ahead and plug your numbers in. Plug your numbers in and get our answer. Again, we forgot to put that negative number, so choose the positive number. Choose the positive one for your answer. It does look like a surprise face, and I was just going to say that, Mrs. Larkin. If you do have, and I'm going to go ahead and turn off the chat box, if you do have any questions, those chats will come privately so we can also help you out in that particular area. I'm going to put 45 seconds up on the clock to go ahead and work this problem. This will be our last problem, and then we do need to, for some reason, I think we're doing like excellent on time right now because period 3 is on point. Nice job, everybody. Green checks when you have this answer locked in. Green checks when you have this answer locked in. Remember this magic number right here. And you have your time and then starts at rest. I know you have got this. Look at those questions. Didn't even need to look at the didn't even need to look at the problem. You knew it. You got it. Well, don't guess, but, you know, I'm glad that it's coming so easily for you. Awesome job. Again, seeing those green checks flying up. Excellent job, period 3. I love it. Here we go. All right, let's just go ahead and check. Awesome, Harmony. Antoine, woo, woo, nice job. That's okay, Greta. You know, that's all right. That's all right. Remember, when you look at the problem here, acceleration due to gravity, where does that go? Here's what the problem or the formula looks like. You should know that velocity. That initial is starts at rest. Good. Awesome, Brisa. All right, let's go ahead and look where else we got. Let's see. Awesome, Sally. That is correct. We agree with you. And Haley, awesome job. So now, Greta, just go ahead and plug those numbers in and multiply. All right. Feeling good. All right, let's go ahead and move on. I feel pretty confident that everybody has got this. Again, if you do need some more time to digest it, take a picture of it and then always come back to it and redo it. And like always, recording comes out between the hours of 1 and 2. You can always go back and look at those examples later. All right, so let's look at this. A lot of you have already submitted your 2H assignment. Awesome job for those A's. I see those A's and B's flying up there. Awesome, great job. Super proud of all of you. Looking good. Awesome, awesome. Awesome possum. I can't say it enough. Good job. All right, here we go. Today we talked about the effects of gravity on free fall and Newton's second law. We also calculated that velocity on objects in free fall on Earth. We did that through our 2H notes. And I'm going to go ahead and hand it over to Mrs. Larkin so she can talk about our project.
All right, everybody. So at this point, we do want to be making sure that we're getting our projects ready. So you don't have live sessions tomorrow. So we will be sending out instructions as well as a template tomorrow for your egg and water balloon project in particular. If that is the project you're doing, please make sure that you begin building your cage for your egg and water balloon. Again, the idea is that you're going to try to drop it from a high place and prevent it from breaking by building a good cage. And again, you can research anything from Google that would help you make a good cage for that, and you can use whatever materials you want. Okay, and make sure that this is ready by Friday. That way you can go ahead and drop it and get all of your data, and then you'll be able to work on it over the weekend and Monday and submit it on Monday. Okay. All right, so yeah, it doesn't have to be super crazy complicated. Don't go crazy with it unless you would like to. You are absolutely welcome to go crazy with it, but you don't have to. Okay, so here's what we're going to talk about. The final velocity of an object in free fall can be calculated based on the equation we took a look at today. So what everybody needs to do for your project is, whether you are doing the egg, water balloon, or ball project, or virtual ball project, yes, there's still a virtual ball project, you are going to go ahead and take a real ball, and you're going to go ahead and find a high place where ideally you would drop your egg or water balloon or ball from, and you're going to time how long it takes for the ball to hit the ground. Okay, don't actually use your egg or your water balloon. Please start with just using a ball. If for some reason you don't have a ball, you can use any item, all right, as long as it's not a feather. So any item that falls like a ball, that's totally fine. The same thing if you're doing the virtual one, you still need to do a real example of dropping something. Okay, so use your phone or stopwatch to time how long it takes for the ball from your chosen height to hit the ground. Okay. And again, for the egg, water balloon, that should be a pretty high height. And for the ball, I would still recommend a pretty high height. That way it falls for long enough that you can actually time it. Okay. So here we go. Let's go ahead and talk about the things that we need to know for this equation. Again, what is the initial velocity? Tell me in the chat box. If we're just holding it and then we drop it, what's that starting velocity? Like every example we saw today. What is the initial velocity for everything we saw today? Yeah, this is going to be our 0 meters per second. And what is the acceleration due to gravity? Always on Earth. This is our magic number. Yep, that's going to be negative 9.8 meters per second squared. Beautiful. And again, the time, this is what you're going to measure with the stopwatch. All right, so this is what you should measure with the stopwatch, either on your phone or a real stopwatch if you still have a real stopwatch. I don't know who still has those. Now, for a lot of you, your time might actually end up being less than 1 second. So if you see something like this where it says 0.71, that is 0.71 seconds. So that will be less than a second, but it's okay. That will still work for your calculation. Okay, and once you know all of that, you should be able to calculate final velocity. So that'll be the expectation tomorrow when we send out the template, one of your slides. You are going to be timing dropping an object from your designated drop point, and you are going to go ahead and calculate the final velocity of that object as it hits the ground. All right, in the chat box, please go ahead and give me a star if that makes sense. Star if that makes sense. Even if you're doing virtually, everybody has something that they can drop. Everybody should be able to time how long it takes for something to drop. So even if you're doing it virtually, you still have to do this part physically. Cool. All right. So that being said, I'm going to go ahead and drop this up on the whiteboard because this is going to be our answer for today's attendance. Here we go. So today's attendance is those first two parts. So you don't answer all of this. You just need to answer the first two parts. And that is, what is the initial velocity of your egg, water balloon, or ball? And what is the acceleration due to gravity on it? That's going to be these first two parts right here. All right, so initial velocity is 0 meters per second since it starts at rest. And acceleration due to gravity is negative 9.8 meters per second squared because it's falling on Earth. There you go. Go ahead and click on the link, start a new thread, answer both parts of that, and then you are good to go. See you all later. Have a wonderful day. We won't see you tomorrow. Make sure you watch the recording though and get started on your project tomorrow. And then Friday we'll see you back in class. Bye everyone.